Welcome to Part 5 of Section 3.4. Here we're going to be finding not only just the real roots of polynomials, but also the complex zeros as well. We've already learned by the fundamental theorem of algebra that a polynomial's degree is the same as the total number of roots or zeros that it has. Roots, we've also learned, can be either real or imaginary. Now, our textbook calls them complex. We see that although complex and imaginary numbers aren't exactly the same, they're enough in similarity that we can kind of use those words interchangeably. Basically, a number that has an I in it, we either can call imaginary or complex. So your book is calling these zeros complex, and I have been referring to them as imaginary. They are the same thing, just so you know. All right, let's take a look at exploring our first polynomial. I've made it simple. This is a quadratic function. So let's talk about just a couple things we know about this. We know that its degree is 2. We know that it's going to be a parabola. And by the fundamental theorem of algebra, we know that it has 2 total roots. And like I've already said, those roots can either be real or imaginary, and imaginary roots have to come in pairs. So out of those 2 total roots, we have options. Option 1 is that both of the roots are real. So we have 2 real roots, and none of those 2 are imaginary. Option 2 is that both of those roots are imaginary, and neither are real. We cannot have only one real root and one imaginary root out of the 2 because imaginary roots come in pairs. So these are the 2 options that we have. Now before we get into anything more algebraic, let's just take a look at what this function looks like, and that'll allow us to determine whether they're both real, meaning they'd hit the x-axis, or they're both imaginary, meaning they don't. I have graphed f of x, and we can clearly see that we have no part of our parabola hitting the x-axis. Therefore, the roots are both imaginary. We cannot find them by just looking at our graph and seeing where our parabola hits the x-axis. So instead, what we're going to have to do, we'll use the quadratic formula, and we will have I in our final answer. So what we've determined by looking at the graph is that yes, it's degree 2 and it has 2 total roots, and they're both imaginary since we do not have any part of the parabola that hits the x-axis, no real roots. So we are going to not have to do any synthetic division because we already have a quadratic, and that is ultimately the goal of synthetic division, is to get it down to a quadratic. We have a quadratic, so we can use the quadratic formula to find all of our roots or zeros. So we can use the quadratic formula once we have a quadratic. We know that A is 3, B is 2, and C is 10. Using the quadratic formula, we'll take the opposite of b, so negative 2, plus or minus the square root of b squared, or 4, minus 4 times a times c. I do recommend you have the quadratic formula written down and easily accessible in your notes. It is then all over 2 times a. All right, from here we'll have negative 2 plus or minus the square root of 4 minus, whenever there's a 10, do that last. That's the easiest multiplication. 4 times 3 is 12. Put a 0 on it, 120. So we have 4 minus 120 all over 6. Now 4 minus 120 is going to give us negative 116, and that is all over 6. When we learned about the quadratic formula back in Chapter 2, we learned that the value that's under the square root is called the discriminant. When the discriminant was negative, we had 2 imaginary roots, and that's exactly what we have. So in order to break down the square root of 116, we're going to need an I. So we'll have negative 2 plus or minus, then we need to break down the square root of 116. To break down the square root of 116, we know that we're going to have the square root of 116 and then the square root of negative 1. Now, 116 is not a perfect square. Therefore, we're going to have to break down the square root of 116. The biggest perfect square factor of 116 is actually 4. And 4 times 29 gives us 116. So we'll have root 4 root 29 to give us the root 116, and then root -1, which is I. When we keep going, we have that -2 plus or minus. The square root of 4 is 2. The square root of -1 is I. And the square root of 29 cannot be broken down anymore. And then that is all over 6. I wrote the I first because we don't want it to look like the I is under the square root. And so you want to bring your plain old number out front and the I out front as well. The root should be the last thing written in an expression. Now, can we simplify all three of these? -2, 2, and 6. Yes, we can do the triangle simplification here and divide them all by 2. When we divide them by 2, this will turn into a -1. This will turn into a 1, so we don't need to write it. And the 6 will turn into a 3. And we can leave our answers just like this. But note that these are our two imaginary roots. The plus or minus gives us those two solutions. Next, we are going to take a look at a higher order polynomial, meaning greater than a degree of 2. This is a cubic polynomial. It is degree 3, and by the fundamental theorem of algebra, we know that f of x has 3 total roots. Now, since it has 3 total roots, those roots can either be all real, so option 1 is that there's 3 real roots and 0 imaginary. And option 2, since imaginary roots have to come in pairs, one of those roots could be real and 2 of them imaginary. That means that this function has to have one real root, meaning that in order to find out what that one real root is, we are going to be using the rational zeros theorem with the p over q to find it. We do not have to do a ton of tests. I know that a lot of us are looking at the graph, which is great. That's an awesome resource to have, is looking at the graph of a function. So what I'm going to do is to find that one real root. I'm going to do all the factors of 13 divided by all the factors of 3, like we learned previously in this chapter. So I've listed all of the factors of 13, those are the p-values, all of the factors of 3, those are the q-values. Then our possible rational roots, because we do definitely have at least one real root, and if it's rational, the possibilities would be any of these p's divided by either of the q's. So let's list those. We have 1 over 1, which is 1, and we have 13 over 1, which is plus or minus 13. Then we'll put both of them over 3, plus or minus 1/3, and plus or minus 13/3, which is 4 1/3. Now, instead of doing synthetic division to test all of these to see which one gives us the remainder of 0, let's take a look at the graph and see what's closest. Now, this function is real weird. I just grabbed it. I got it from your book, and it's so weird. It almost looks linear because these numbers are so big and just strange that it is cubic still. It does have a little squiggle if you zoom out enough, but anyway, let's take a look at what our one real root is. It looks like we don't cross the x-axis more than one time. The furthest that it could cross the x-axis would be -13 or -14 to 14 using Cauchy's bound, and we don't cross past those. So it looks like we only cross one time. So one of these roots is real, so the other two are imaginary. It looks like it's at positive 1/3. So let's check that using synthetic division, and then we'll get us down to a quadratic. Okay, so we have determined that positive 1/3 is most likely the one real root, and the other two are imaginary. Let's test that. So let's try our first real root of x equals 1/3. We're going to be using synthetic division with 1/3. So we'll put 1/3, then we'll have our 3, -13, 43, and -13. Bring down the 3. 3 times 1/3 is 1. When we add these together, we'll get -12. -12 times 1/3, we're taking 1/3 of -12. That's -4. Adding those together, we'll get 39. and 1/3 of 39 is positive 13, and that worked. So x equals 1/3 is our one real root. It happened to be rational. Now what we have is a quadratic. Since we started with a cubic, we had to do successful synthetic division one time to bring it down to a degree 2 polynomial, a quadratic. Once you have a quadratic, we have 3x squared minus 12x plus 39. Once we have that quadratic, we can use the quadratic formula. This is definitely not factorable. How do we know that? Because we know that the other two roots are imaginary, and we have to use the quadratic formula for it. So let's use our quadratic formula on this quadratic here. We know that a is 3, b is negative 12, and c is 39. We set this quadratic to 0 technically. All right, so we have the opposite of b, which is 12, plus or minus the square root of b squared, which is always positive, minus 4 times a times c. We can see that our discriminant will definitely be negative, all over 2 times a. When we do the math under the root, our discriminant ends up being negative 324, and then it's all over 6. 324 actually is a perfect square. It's negative, so we'll end up having an I in there. So I will do this in a lighter color here. Okay, when we go to the next line, we'll have 12 plus or minus something all over 6. That something will be breaking down the root of negative 324 into root 324 times root negative 1. We do not have to break down the square root of 324 anymore, again, because it's a perfect square. Its square root is 18. So we'll have 12 plus or minus, the square root of 324 is 18, and the square root of negative 1 is I, all over 6. Now from here, can we triangle simplify? 1, 2, 3. Yes, we can divide all of these by 6. When we do that, we'll divide the 12 by 6 and get a 2. We'll divide the 18 by 6 and get a 3. And we'll divide the 6 by 6 and get a 1, which we don't have to put because it's a 1 in the denominator only. So our two imaginary roots are 2 plus or minus 3i, and our real root we found earlier was 1/3. So here are our 3 roots of our cubic function, 2 imaginary roots, 2 plus 3i, 2 minus 3i, and 1 real root that is rational, 1/3. Here is our third and final example. This one is a quartic function, meaning it's degree 4. By the fundamental theorem of algebra, we know that we have 4 total roots. So we have a couple options for what these roots are. The first option is that all 4 are real and none of them are imaginary. Now that's probably not the case because look at the title of this section. The second option, since imaginary roots come in pairs, is that 2 of them are real and there's a pair of imaginary roots. The last option is that none of those 4 roots are real and there's 2 pairs of imaginary roots. All 4 of them are imaginary. So we have a couple different options. Let's take a look at the graph of this, and then we can use some of the other skills that we have from this chapter to determine where to start. When we take a look at this function, it really just looks like a quadratic. It looks like a parabola, which is essentially what degree 4 polynomials are. They're skinnier parabolas, but we see that we only hit the x-axis once. However, take a look at the multiplicity of this 0 here. We can clearly see that it is a multiplicity of 2, meaning that we do have 2 real roots. The other 2 must be imaginary. This root occurs twice. What I want to do now is, since we know we have this option right here, that's how our 4 total roots are, what we need to do in order to determine what that real root is with multiplicity 2 is use our rational zeros theorem to see what the possible rational roots are. The factors of p, which is 3, the p-values are plus or minus 1, plus or minus 3. The q values, the factors of 4, our lead coefficient, are plus or minus 1, 2, and 4. When we list all of our p over q's, we'll list everything over 1, so 1 and 3 over 1. Then we'll list them over 2, so plus or minus 1/2, plus or minus 3/2. Then we'll list them all over 4, plus or minus 1/4, and plus or minus 3/4. Let's see what this looks like here. It looks like we're at a half. So what I'm going to do is use synthetic division twice to knock this degree 4 polynomial down to a degree 2, a quadratic, and we'd have to use that root of 1/2 twice if it works, because it occurs twice. So let's get on that with synthetic division. Okay, we think that positive 1/2 is the winner. Let's see if it is. What we're first going to do is do synthetic division with 1/2 to see if it works. We'll have 4, -4, 13, -12, and 3. If this works successfully, we'll knock it down to a cubic. Half of 4 is 2, adding those together. Half of -2 is -1, add those together. Half times 12, or half of 12, is 6. Add those vertically, we get -6. Half of -6 is -3, and it worked, which is awesome. So this right here is now our cubic function, 4x cubed minus 2x squared plus 12x minus 6. These we don't even need to write with those x values I just said, because these are just going to be the values we use in our next synthetic division. Since we saw that x equals 1/2 is a root with multiplicity 2, we have to do synthetic division twice for it. Let's do synthetic division again with it to knock it down to a quadratic. And we're going to use these coefficients of the cubic instead. We'll have 4, -2, 12, -6. We bring the 4 down. Half of 4 is 2. Add those together. Half of 0 is 0. Add those vertically. Half of 12 is 6. And it works. So yes, 1/2 was a root with multiplicity 2. Those were our 2 real roots we just found. Now we have a quadratic. We can find those 2 imaginary roots using the quadratic formula. We have 4x squared plus 0x plus 12 equals 0. I know I've mentioned this before, but the equals 0 is not because of the 0 here. It's because in order to solve a quadratic, we set it to 0. Now, the cool thing about this quadratic is you do not need to use the quadratic formula. Why? Well, we don't have a b. B is 0. And since we don't have that linear middle term, we can just solve this straight up if you want. Now, you can still definitely use the quadratic formula if you like, a, b, and c. However, I'm going to show you an alternate way that's a little simpler when you don't have that linear term. And there's definitely alternate ways of doing it than just straight up solving it algebraically as well. We could have factored as well. So I'm going to divide both sides by 4. When we have this now, we'll have the square, we have to take the square root of both sides to solve for x. So we'll have x equals, we need a plus or minus, the square root of -3. So we'll have the square root of 3 times the square root of -1. So x equals plus or minus root 3 times an I. And we mentioned previously that the I, so it doesn't look like it's under the root, should be written first. And those are our 2 imaginary roots. Had you done the quadratic formula with a, b, and c, you would have still gotten here in the end. That might be a good practice for you if you need some extra practice with the quadratic formula. So, of our original polynomial, f of x, the 4 roots are x equals 1/2. It has a multiplicity of 2. And we also have plus or minus I root 3. So our polynomial of degree 4 by the fundamental theorem of algebra has 4 total roots. 2 of them are real. It had a multiplicity of 2, 1/2 did, and the other 2 are complex. All right, so we've talked about a lot of different ideas in this video. The things that helped the most were using the fundamental theorem of algebra, so using the degree and the fundamental theorem of algebra to determine the total number of roots. We then listed the options of types of roots, meaning how many were real, possibly, and how many were imaginary. Imaginary roots had to be an even number since they always come in pairs. The next thing that we did is we looked at the graph to determine how many real roots we had. So we looked at the graph. The graph is your friend. It's not cheating by any means. So we looked at the graph, and we also used the rational zeros theorem to determine the possible real root or roots. Now from there, once we determine the possible real roots, we use synthetic division to knock our polynomial down to a quadratic. Now, how many times do you have to do successful synthetic division? Successful meaning a remainder of 0. It depends on what your initial degree was of your polynomial. You have to do synthetic division however many times it takes to knock it down to a quadratic. Every time you do synthetic division, you knock your degree down by 1. So if it's a cubic polynomial, you only have to do the successful synthetic division once to knock it down to a degree 2. If it's a quartic polynomial, degree 4, you need to do successful synthetic division twice, and so on. You definitely will not get anything bigger than a degree 4. So the most amount of times you have to do successful synthetic division would be twice. Once you get it down to a quadratic, you have to solve a quadratic. And how do we do that? Well, there's different options for solving quadratics. We have done 2 of them in this video. The first 2 examples, we used the quadratic formula because we had a, b, and c, and none of them were 0. Well, b was not 0. In the third example, with our quartic polynomial, when b is 0 and you don't have just an x term, you can just straight up solve it algebraically because you don't have that x in the way. Normally, an option is also to factor, but since in this section we're dealing with complex zeros and not rational ones, we cannot really have, we don't have the opportunity to factor because they're not factorable. So in order to solve the quadratic, the option that always works is the quadratic formula. So if you're ever wondering another way to solve and you're not sure, the quadratic formula is your friend. Definitely make sure you have that down. All right, this was our video of finding complex zeros. There are a ton of great problems in your textbook that I highly recommend that you take a look at, especially the ones I recommend on the assignment. Good luck.